The other day, I had you guys do an inverse function review, and we did discuss inverse functions at the beginning of the year. And in order to have inverse functions, we know that we kind of have to have a few things in place in order for a function to have an inverse. And that is that the function has to be one-to-one. And in order to be one-to-one, it has to pass a vertical line test as well as the horizontal line test. So what we are going to do is kind of look at and go through these ideas and concepts. So inverse functions, if you recall from your past math classes in the beginning of the year, are represented by a set of ordered pairs in which the domain and range interchange. So what that means is on the original function, the domain becomes the range of its inverse, and on the inverse function, it flip-flops. The range becomes the domain, etc. So a horizontal line test allows us to compare these kind of algebraically. The horizontal line test says a function is one-to-one if and only if no horizontal line intersects its graph more than once. So what that means is for every x there is only one y, and for every y there is only one x. So again, for every x there is only one y, and for every y there is only one x. An inverse function uses that notation in which you have f raised to the -1 power. And I always stress about how that f raised to the -1 power is not signaling or signifying 1 over f. It's implying the inverse of f. So that leads us into the existence of an inverse function. So in order for a function to have an inverse, the function must be one-to-one. If the function is one-to-one, we can determine if it is one-to-one by the horizontal line test, and then we move on and graph it. So we have two functions. We have x cubed and x squared. X cubed is graphed here in red. X squared is graphed here in blue. What you'll notice is x cubed is odd. That makes it symmetric about the origin, and thus one-to-one. Therefore, x cubed will have an inverse. X squared is even. It's symmetric with the y-axis, and therefore it will not have an inverse, and it is not one-to-one. So again, on your paper, I gave you two separate graphs to draw those in. On mine, I just kind of did them on one. To find the inverse of a function, we have to determine if the function is one-to-one. If the function is one-to-one, then we switch the x and y values, solve the equation for y, define the two domain and ranges, and verify that the companies of the two functions are going to equal x. So we're going to do function composition. So again, everything so far we're talking about is the old finding an inverse of a function algebraically. Okay, so we can show that a function is an inverse of each other by sketching the two functions and comparing their set of axes. So we have f of x equals 2x squared minus 1, and g of x equals the square root of x plus 1. So what we do is graph each of these. So f of x is going to be a quadratic. It is shifted down 1. So what that means is my vertex is 0, negative 1. And then instead of going up and over 1 like our normal, it goes up 1, 2, and over 1. And then our other point, instead of going up 4 and over 2, it'll go up 8 and over 2. So there's our graph, and then again it says sketch both functions on the same set of axes, and we want to sketch g of x. So that square root is really like 1/2 x plus 1/2. So what that tells me is that this graph is moved 1 unit to the left. So it's going to go through our point when x is 0 of 1/2. And then it's also going to go through the point when x is 1 of 1. And when x is negative 1, it'll go through 0. So what you'll notice is that the original function f of x equals 2x squared minus 1 is not actually going to have a true inverse of g of x, because of the idea that it is not 1-to-1. However, we can limit the domain of f of x in a way that f of x is only graphed for x values greater than or equal to 0, because g of x is only the positive square roots. So what we're going to do is restrict the domain of f of x. So we'll leave that on, and we'll use blue to show that if we restrict the domain of f of x such that f of x is only positive, therefore making f of x 1-to-1, and by making f of x 1-to-1, f of x has an inverse. And in this case, that inverse is g of x. We could compare the two algebraically by plugging g of x into f of x. So again, I just need some space, and what we could do is take f of g of x, and that would give you the square root of x plus 1 over 2 squared times 2 minus 1. And we can ignore the 2 out in front. A squared square root goes away. So that gives 2 over x plus 1 all over 2 minus 1. So now your 2's cancel, and that gives x plus 1 minus 1, which leaves you with x, which does in fact confirm that this is a inverse of the function. But again, we know the only way for it to have an inverse is to be 1-to-1, which means we need to restrict the domain of f of x to be x greater than or equal to 0. Okay, find the inverse of the function f of x equals x cubed plus 2. So again, we are looking to find the inverse of this function. So in order to do that, we are going to use the steps from the front. So that means where we had f of x, we're going to make it x. And where we have x, we are going to make it y. So we get x equals y cubed plus 2. And now we're going to solve for y. So we subtract 2 from both sides. And then to get something that is cubed to be non-cubed, we're going to take our cube root of both sides. So the cube root of y cubed becomes y. So we get y equals the cube root of x minus 2. And the cube root of x minus 2 is thus considered the inverse of f of x. And that is our answer, because again, we're just finding the inverse of that function. We know that x cubed had an inverse because it was 1-to-1. So x cubed shifted up 2 units will also have an inverse because it will also be 1-to-1. It will just be shifted up 2 units. How are we sure if a function is an inverse of another function? Well, the way you can determine if two functions are inverses is by doing their function composition. So what I can do is compose f and f inverse with each other and see that I get the identity function x. Or I can do f inverse composed with f and also see I get the identity function x. So again, the idea is that we are able to find inverses by switching x and y, and then we can determine if two functions are inverses by simply looking at their composition. If their composition is x, then we know that we have found the inverses. Okay, so one last example. Now we're going to look at derivatives and inverses together, and we're going to create the connection between the two. So we do have to recall the reflexive property of inverse functions that states the graph of f contains the point AB if and only if the graph of f inverse contains the point BA. So that's going to be really useful in looking at this example here. So it says find the inverse of the function x cubed. So we did all that, sorry. Find the inverse of the function y equals 4x plus 1. And we're going to find the derivatives. So what is the slope of the original? The slope of this graph of this line right here So again, we can use the concepts from the previous example to find that the derivative of the inverse function exists without having to find the inverse, because we can simply find the derivative of the original, differentiate the original at a point A, so that becomes f prime x at x equals A, where it stands for the derivative of f with respect to x at point A. To find the derivative of the inverse at that same point, we find the reciprocal of the derivative of f at point QP. So that's why I said you're going to invert your points. And then you are going to compare, so the derivative of the inverse with respect to x at point P is equal to 1 over the derivative of f at point Q. So to find the derivative of the inverse at point P, we find the derivative at point Q. So to find the inverse derivative at P, we find 1 over the derivative at Q. So again, I repeated it a few times. Take a minute to absorb that, because it's very critical as we work through our next problems. So, we have f of x equals x cubed plus 2x minus 1. We want to find 0, negative 1 on our graph. So let's start with f of 0 and confirm that it equals negative 1. So we verified our point. So that's kind of like my P and my Q. So part B asks me to find f inverse prime at negative 1. So I am looking for the inverse derivative at negative 1, which into my formula is kind of like saying 1 over f prime of the original point flip-flop. So if this is negative 1 on my derivative inverse, then that's like 0 on my original. So in order to find that, I need to know what f prime of 0 is. So in order to get f prime of 0, I need to know what f prime of x is, which it is 5x to the 4th plus 2. So f prime of 0 is 2. So f inverse prime of negative 1 is 1 over 2, or 1/2. Okay, f of x equals x cubed plus 2x minus 1. Find the derivative's inverse at 2. So again, this is kind of like the y value of my original. So that's the y value of the original. So in order to find the x value, I'm going to have to find where that function equals that y value. So we're kind of looking for an intersection. We're looking for the intersection of y equals 2 for y equals x cubed plus 2x minus 1. So we know that to solve or find intersections of any functions, we have to set the function equal to 0. So I get x cubed plus 2x minus 3. Unfortunately, this isn't a case where it's easy to factor because it's an x cubed. So now I need to know, where does this cubic equal 0? So you have to go back and use the rational root theorem, which says that the factors of the last term over the factors of the first term are whole rational roots of this problem. So what that means is that my potential roots could be 1 or 3. So I'm just going to quickly kind of try to plug those numbers in and see if any of them get me to 0. So if I plug in 1 cubed plus 2 times 1 minus 3, does that in fact equal 0? Well, 1 plus 2 is 3. 3 minus 3 is 0. All right, I got super lucky that when x is equal to 1, y will equal 2. And again, you could confirm that by plugging it in way up here. 1 plus 2 is 3. 3 minus 2, or 3 minus 1 is 2. So it in fact works. So what that means is on my original, I have the point 1, 2. So on my original, I have the point 1, 2, which means for my derivative and my inverse, this is kind of like saying df inverse dx at 2 is equal to 1 over f prime at 1. So that tells me that I need f prime and I need f prime at 1. And my inverse is 1 over 5. So what I want to do is take a minute and pause here before. So this is called method 1. There are 2 methods for finding the derivative of a function. This is method 1. So I just want to reiterate and review that method 1 involves taking the original point, finding the derivative of the original function, and then inverting the point at which you're finding the derivative at. So if I'm finding the derivative at 2, then on the original, I'm looking for f prime of its partner. Okay, so let's move on to the next part of this unit, which is looking at method 2. So method 2 is a little bit different than method 1. Method 2 can be used when finding the inverse of a function that is messy. So method 1 is really nice and useful when we're looking for inverses of polynomials, because their derivatives are easy. Finding their flip-flopped points is easy. Finding the inverse of a function that is not so easy involves using the steps we learned and reviewed at the beginning of class today, which is to actually change your x and y, find your inverse, and find the derivative of the inverse. The reason we learn inverse derivatives after implicit differentiation is because we can use techniques from implicit differentiation to help us find these messier inverse derivatives. So we're going to use the idea and the techniques behind dy dx and implicit differentiation to find these messy derivatives of inverses. So we're just going to jump right on into a problem. Method 2 doesn't have a formula like method 1. So method 1, you kind of followed into that formula. Method 2 goes back to what we did at the beginning of class, which is to find the inverse. So we're going to take y equals f of x equals x cubed minus 4x squared plus 7x minus 1. So we take y equals x cubed minus 4x squared plus 7x minus 1. And then to find its inverse, you're going to flip x and y. And this is why I said understanding and knowing implicit differentiation is really important, because you don't want to solve this red equation for y. It would be really messy and really gross. So by just taking the derivative of the inverse, we'll be able to find our inverse derivative. So the derivative of x is 1. The derivative of y cubed is 3y squared dy dx minus the derivative of 4y squared, which is 8y dy dx, plus the derivative of 7y, which is 7 dy dx, and the derivative of negative 1 is 0. So just like back in the day when we did implicit differentiation, we're going to factor out dy dx, leaving me with 3y squared minus 8y plus 7. And then just like in implicit differentiation, you're going to solve for dy dx. And that red function now represents the inverse derivative. That now represents the inverse derivative. So we're asked to find the inverse derivative at x equals 1. So what you'll notice is all of my inverse derivative is in terms of y. So in order to be able to find the inverse derivative at x equals 1, I need to know what y is when x is 1. So f of 1 is equal to 3. So again, what this question is asking, it's asking me to find f's inverse at 3 as the derivative. So we are looking for f inverse prime at 3. So plugging that in, that's dy dx at 3. So go ahead, take a minute and solve that. And you should get 1/10. Okay. If f of x equals x squared and x is greater than or equal to 0, find the derivative of f inverse x at x equals 4. So again, we're trying to find the derivative of f inverse x at x equals 4. So that's like d dx of f inverse at 4. But 4 is not the y value in this case, it's the x value. So now I kind of need to find the y value. So we're going to plug that 4 in to my original. So f of 4 is 4 squared, which is 16. So what that means is we're really finding f inverse derivative at 16, because 16 is the y value. And once again, if we use our new method, it would be like saying x equals y squared. The derivative of that is 1 equals 2y dy dx. And then you get dy dx equals 1 over 2y. And that gives 1 over 2 times 16, or 1 over 32. And that is your inverse. Derivative. So again, the connection between the derivative of an inverse function using method 1 and method 2 can be streamlined down here. So what you can see is that it's f prime of f inverse down there. It's f prime of f inverse. Okay, I don't think you have to copy anything down, right? No, I copy and pasted that for you. So then the next one is find the inverse using that formula above. So we have f of x equals 1/4 x cubed plus x minus 1 at x equals 3. So again, streamlining our process and plugging in using that formula. We need to know what is the y value at x equals 3. Okay, sorry. If we have f of 3, so 3 cubed is 27, 1/4 times 27 plus 3 minus 1, well 3 minus 1 is 2, and then 27/4 plus 2 is really like 27 fourths plus 8 fourths. So we can add those two values together and get down to a simple fraction of 35 fourths. So you have f prime of f inverse x. So f inverse x is like 3. So f prime of f inverse of 3, well the inverse of 3, sorry, not 3, 35. I jumped ahead. The f inverse of 35 fourths ends up becoming f prime of 3. Because again, we look for the inverse of the y because the inverses are flip-flopped. So really you're finding f prime at 3 for this function in order to use that formula. So f inverse prime of 35 fourths is equal to 1 over f prime of 3, which is method 1's formula. Which becomes 1 over 1/4 3x squared plus 1, or 1/4 3 times 3 squared plus 1, or 1 over 27 fourths plus 1, which is 31 fourths, or 4 over 31. Okay. You could compare that method to finding it using the inverse derivative, which is flipping your x and your y's. So again, we know that if we flipped our x and y's, that would give x equals 1/4 y cubed plus y minus 1. So you'd get 1 equals 3/4 y squared dy dx plus dy dx, or 1/3/4 y squared plus 1. And in this case, since we're looking for f inverse of 35/4, my y value is kind of like the x value. So when you find it using the streamline formula this way, you're actually plugging in that original 3 for y, because that 3 is the original, right, point of x. So that means on the inverse, that 3 is our y. Oops, you can't see what I'm writing in here. So that 3 is the original 3 for x in our domain. So the original point is 3/35. So the inverse point would be 35/4 comma 3. So what that means is when I plug that 3 in down here, that is my y value, because that x equals 3 is from the original. So that means on the inverse, that x equals 3 becomes my y value. So down here, plugging in, so you could compare the two methods, you actually plug 3 in for y. So you have to be careful of where you're talking about your points and if they're the original or the domain. So the derivative of the inverse of 35/4, remember that formula, that makes this the x value in terms of plugging into that formula, even though it's the y value of the original. So I know that's where it gets kind of messy, and that's why I wanted to do this problem both ways, is to show how that x value is the original and or the y value of the inverse. Does that help kind of create clarity as to what value you plug in where? And again, the more you practice it, the more it's going to make sense. And the next example with the table, I think really helps create that clarity, because it helps you really see how the points are the inverses and originals. So we have a table, and we want to find the inverse derivatives using those formulas or methods. So this problem is asking me to find the inverse derivative at 1. Which means this is like finding 1 over g prime of g inverse of 1. So again, if you go back to the concept or the page we just talked about, when we were looking for that derivative at 35/4, that was the y value of the original, which made the 1, here, can I pull it back up? Let me just go back. Okay, so again, taking into account this comparison, here we said at x equals 3. So when you plugged it into your formula, it looked like f prime f inverse of 35/4, but became f prime of 3. So in this problem here, you actually don't even really need to know what G inverse is, because you're looking for f prime of 3 on the original. So my original point is 3/35. My inverse point is 35/4 3. So in terms of this problem here, if I'm looking for G inverse prime of 1, and we're comparing it to what we were looking for here, that 1 is the y value of the original. So that 1 here represents the y value of the original. So in order to use this table, this is the y value of G of x. So I need to know, like, when does G of x equal 1? So G of x equals 1 at -1. So this is kind of like saying G of -1 equals 1, which means in terms of plugging it in, this is like finding 1 of G prime of G inverse of 1, which is really like finding 1 of G prime of -1, because that's my x value. So that's 1 over G prime at -1, which is -1/5. So this is really -5. So again, this represents the y value of the original. So that's -3. So that means I'm looking for 1 over G prime of 4. Which is -1/2. We are pausing there. The next thing you're going to do is some review problems. So it's the homework day 1. It has NIMSY at the top of that page. It says the derivative of an inverse function. What I did is at the top of that homework, I put all the formulas we talked about today, using implicit, using method 1, using method 2, really discussing how they coordinate to each other. So you'll see that on this handout here. There's our important formulas. There's composition, taking into account that the inverse and the composition make x. Finding the derivative of both sides of those. So again, using function composition to get down to this formula. So if you wondered where I got that formula for method 1, here is the actual calculated calculus steps to finding it. And then what I want you to do is work on their sample questions. So you're doing that page. The next page with like the table like we used. And then you're doing the 8 problems on the inverse of a function. And then we'll pick up with the derivatives of an inverse function on Tuesday. So you have those 6-ish problems, because one is A, B. So you have to do 1 through 5 on the NIMSY and 1 through 8 on the derivatives of inverse functions.